Now we'll take a look at some special purpose diodes. In addition to the general purpose rectifier diode previously covered, other diodes are used for special purposes. These diodes include the Zener diode, the varactor diode, and LED or light emitting diode and photodiode. The Zener diode is used to regulate voltages for reference purposes. The varactor diode is used as a voltage variable capacitor. The LED emits light when forward biased, and the photodiode is used to control the amount of reverse current with light. A major application of the Zener diode is to provide an output reference voltage that is stable despite changes in input voltage. Reference voltages are used in power supplies, voltmeters, and other instruments. You can see the diagram on the right for the Zener diode, the schematic. The Zener diode is a silicone p-n junction device that differs from the rectifier diode in that it is designed for operation in the reverse breakdown region. The breakdown voltage of a Zener diode is set by carefully controlling the doping level during the manufacturing process. From a discussion of the diode characteristics curve, recall that when a diode reaches reverse breakdown, its voltage remains almost constant even though the current may change drastically. This volt amp or VI characteristic is shown again with normal operating regions for rectifier diodes and for Zener diodes shown in the shaded areas. If a Zener diode is forward biased, it operates the same as a regular diode. So there's the diagrams right there. So you can see the normal operating regions for a rectifier diode as shown in the shaded areas, and then the normal operating region for a Zener diode then over here on the left. Zener diodes with breakdown voltages of less than 5 volts operate predominantly in Zener breakdown. Those with breakdown voltages greater than approximately 5 volts operate predominantly in avalanche breakdown. Both types, however, are called Zener diodes. Zeners with breakdown voltages of 1.8 volts to cover 300 volts are generally available. The figure below then shows the reverse portion of the characteristic curve of a Zener diode. Notice that the reverse voltage V sub R is increased. The reverse current I sub R remains extremely small up to the knee of the curve. So we can see that here. The breakdown voltage V sub Z remains essentially constant. This regulating ability is the key feature of the Zener diode. A Zener diode maintains an essentially constant voltage across its terminals over a specified range of reverse current values. A minimum value of reverse current ZK, must be maintained in order to keep the diode in regulation. You can see on the curve that when the reverse current is reduced below the knee of the curve, the voltage changes drastically and regulation is lost. Also, there's a maximum current IZM above which the diode may be damaged. Thus, basically, the Zener diode maintains a nearly constant voltage across its terminals for values of reverse current ranging from IZK to IZM. A normal Zener test voltage, VZT, is usually specified on a data sheet at a value of reverse current called the Zener test current, or IZT. Referring to the figures 1650 below, it shows the ideal model of a Zener diode in reverse breakdown. It simply acts as a battery having a value equal to the Zener voltage. In the figure B, it represents the practical equivalent of Zener where the Zener impedance Z sub Z is included. The Zener impedance is actually an AC resistance because it's dependent on the ratio of a change in voltage to a change in current and can be different for different portions of the characteristic curve. Since the voltage curve is not ideally vertical, a change in Zener current delta I sub Z produces a small change in Zener voltage delta V sub Z, as illustrated in C. So we can see that here on the characteristic curve. There's our Z sub C, delta V sub Z, and delta I sub Z. And you can see where it translates to each of those changing parameters on the curve with respect to the knee of the operation. The ratio of delta V sub Z to delta I sub Z is the Zener impedance, expressed as Z sub Z equal to delta V sub Z divided by delta I sub Z. Normally, Z sub Z is specified at I Z sub T, the Zener test current. In most cases, this value of Z sub Z is nearly constant over the full range of reverse current values. In this example, a certain Zener diode exhibits a 50 millivolt change in V sub Z for a 2 milliamp change in I sub Z. What is the Zener impedance? So we just use that relationship, delta V sub Z divided by delta I sub Z, and we get a Zener impedance Z sub Z equal to 25 ohms. Although inexpensive three-terminal integrated circuit voltage regulators provide better performance, Zener diodes can be used for voltage regulation in non-critical, low-current applications, such as providing reference voltages. A basic circuit is shown in the figure to the left. As the input voltage varies within limits, the Zener diode maintains an essentially constant voltage across the output terminals. However, as Vn changes, I sub Z, the Zener current, will change proportionally, and therefore the limitations on the input variation are set by the minimum and maximum current values within the Zener, the Zener can operate, and on the condition that the input voltage Vn is greater than V sub Z. Resistor R in the diagram is a series current limiting resistor. Suppose that a 10 volt Zener diode in that figure 1651 can maintain regulation over a range of current values from 4 milliamps to 40 milliamps. For the minimum current, the voltage across the 1K ohm resistor is as follows. The voltage then across the resistor, 4 milliamps, 1K ohm, is equal to 4 volts. Since V sub R is equal to Vn minus V sub Z, we get 4 volts plus 10 volts, which gives us 14 volts. For the maximum current, the voltage across the 1K ohm resistor then is equal to 40 milliamps times 1K ohm, or in this case, V sub R is equal to 40 volts. Therefore, Vn, 40 volts plus 10 volts, gives us 50 volts. As you can see, this Zener diode can regulate an input voltage from 14 to 50 volts and maintain approximately 10 volts output with no load or a very high impedance load. The output will vary some because of the Zener impedance. As a safety note, Zener diodes are important in intrinsically safe IS circuits, which are used in instrumentation and control circuits that are in hazardous environments, such as around propane tanks. Zeners limit the voltage to a level that is intrinsically safe, which is normally 24 volts DC or less. Thus, potential sparks with enough energy can initiate an explosion and can be avoided.